I toss a coin once, I get either heads or tails. If I get heads, I call it 1. If I get tails, I call it 0. And I get this probability mass distribution. If I toss the coin twice, I can either have 2 times a head, 2 times a tails, or I can have 1 of each. If I add up the tosses, I get a convolution, a self-convolution of the distribution that we've seen in the video on independence. Now I can repeat that. If I toss it 3 times, I get a triple self-convolution. If I toss it 4 times, or 5 times, or 10 times, or 100 times, you slowly see this bell shape forming. This is for 1,000 times. Now, if I add up and then divide by the number of times, then you can see that, well, the width of this bell curve shrinks and the peak is at exactly a half, which is the expected value of a single coin toss. That's not a coincidence. If I take a different experiment, for example, I throw my D20, from my Dungeon Master, a 20-sided dice. If I throw it once, I get this distribution. If I throw it twice, 3 times, 4 times, 5 times, 10 times, 100 times, 1,000 times, again that bell curve. And if I divide by the number of times I've thrown, I again get a very narrow distribution, which has a peak around the expected value of a dice throw. If you had a 20-sided dice, the expected value is at 10.5. And the same happens if I start out with different distributions, even with continuous distributions. If I start out with a uniform distribution and I take it once, twice, 3 times, 5 times, 10 times, 1,000 times, again that bell curve. If I start with an exponential distribution, once, twice, 10 times, 1,000 times, again, if I average out, I get a very thin bell-shaped distribution that is centered around the mean of the original distribution. This is true for a very large set of distributions. Actually, this is true whenever the original distribution has a mean and a variance. That is called the central limit theorem, and I would like to sketch a proof for that theorem in this video. The bell shape you see here is known as the normal distribution. It is described by a probability density function that looks like this. Because it is a symmetric distribution, its peak is also its mode and its median. And for this particular normal distribution, the median or the mean lies at 0 and the standard deviation is 1. But of course we can shift it so that the mean lies somewhere else, and we can also scale it so that the standard deviation becomes bigger or smaller. That way we can adjust it to fit whatever experiment we had, to fit the bell shape that comes out of running a number of experiments. Now, to prove that the running average over a number of experiments indeed converges to a normal distribution, let's write a series xi for the independent, identically distributed variables or stochastic variables that represent our experiment. They are independent because we run the experiment independently a number of times, and they are identically distributed because it's supposed to be the same experiment. If we do that, we can write x bar of n for the running average of the first n experiments and see what happens to the distribution of x bar of n, which is a stochastic variable in itself, when n grows larger. Let's write mu for the expected value of our experiment. We of course have to assume this expected value exists If it doesn't exist, then the central limit theorem cannot possibly hold, because you cannot converge to something that doesn't exist. So the central limit theorem does not hold for all possible distributions. Now, it's easy to prove that the expected value of the running average is itself also equal to mu. If you want, you can just stop the video here and have a closer look at this derivation. In a similar way, if we write sigma square for the variance of our experiment, then it's also easy to prove that the variance of the running average of x bar n is equal to sigma square divided by n. So the variance starts out to be the same as that of our experiment, but if we run more experiments, the variance gets smaller and smaller, and it actually decreases by a factor n, by the number of experiments that we've done. The proof of that, well, just stop the video if you want to study it for a little longer. Our intuition is that the distribution of x bar goes to a normal distribution when n goes when n grows larger. But we've also seen that the variance becomes smaller and smaller while n grows. So if we would let n grow to infinity, the variance would go to 0, and it would be very difficult to compare the distribution to anything else. What we do as a mathematical trick to still capture the intuition that we are going to a converging to a normal distribution is that we're not going to study the variable x of n, but we're actually going to normalize that variable, scale it and shift it in such a way that the variance remains 1 and that the mean becomes 0. And in that way we can show that this normalized variable indeed converges to a normal distribution with mean 0 and variance 1. Now formally, the central limit theorem states that for IID variables xi with expected value mu and variance sigma squared, the sequence Zn converges in distribution to the normal distribution as n goes to infinity. I will sketch a proof of this using some of the techniques that I've discussed in earlier videos in this module. But if you want to know the precise details, you could, for example, go to the website statlec.com, which actually contains a lot more material on probability theory. Now, as we've seen in the video on independence and characteristic functions, if we take the average over a sequence of stochastic variables, independent stochastic variables, it is helpful if we think of them in terms of their characteristic function, because the convolution is only defined on the probability density function or the probability mass function, while if we lift it to characteristic function, or if we perform this Fourier transform first, then the addition of the variables gives rise to multiplication of the characteristic functions. Now, our strategy therefore for proving the central limit theorem is to work with characteristic functions. Well, one thing that you need to know, and you may be able to check that using, for example, Wolfram alpha, is that the characteristic function of the normal distribution, so the characteristic function of this probability density function, is actually given by a power function as well. And the only thing that we now need to set out for is to prove that the characteristic function of z of n converges to this characteristic function of the normal distribution. Of course, the characteristic function of Zn is defined as the expected value of e to the power it Zn, which is equal to e to the power it, the square root of n, times x bar minus mu divided by sigma. Now we can unpack the individual stochastic variables from that x bar to get the sum over these individual variables divided by n. And we can, with some algebraic manipulation, get that division by n outside of the brackets, so that we, well, actually get square root of n divided by n, which is the same as dividing by the square root of n. And we get the expected value of e to the power it divided by the square root of n times the sum over all the variables, but then the shifted and scaled version of the individual variables. Now, that sum in the exponential can also be written as a product of exponentials. So we get the expected value of the product of e to the power it divided by square root of n times the individual shifted and scaled variables. And using, well, this is a little bit of a trick that you may want to check on these Fourier transformations. Using the independence of the xi, we can prove that, well, the e to the power I are independent as well, and that this product, the expected value of this product is actually equal to the product of the expected values. This is the core part, which I'm not going to give into detail, but the core part where actually we use that the sum of independent variables gives rise to a product in the characteristic function. After that, well, let's just replace this shifted and scaled version of xi by a new stochastic variable yi. That cleans up the notation a little bit. And because these yi are all identically distributed, the xi are identically distributed, so the y are as well, we get the product over the expected value of e to the power it divided by square root of n y1. We only need to check one of the different i's. The part on the right is now just the characteristic function of y1, evaluated in the point t divided by square root of n. And if we now take n times the product of that characteristic function, that's just taking that characteristic function to the power of n. So I hope you're still with me on this point, because from this point on I had to brush up my analysis skills a bit myself to understand what was going on. What happens is that when n goes to infinity, t divided by the square root of n goes to 0. And that helps because it means that we can evaluate the characteristic function of y1 around the point 0. That is a continuous function, even if y1 itself is not a continuous stochastic variable. After taking the characteristic function, it becomes continuous. So around the point 0, we can take a Taylor series expansion. Now, I have to admit I copied Marco Taboga's expansion for this. And what you want to pay attention to is the fact that the expected value of y1 is 0 because we shifted and scaled it in an appropriate way. And this helps because it not only removes the term I times the expected value of y times s, that imaginary part, but it also turns the square, the term, the expected value of y1 squared, into the variance of y1. And because we scaled the variance, we know that the variance of y1 is 1. This Taylor series expansion shows us that around the point 0 we can approximate the characteristic function of y by 1 minus a half s squared plus something of an order of magnitude smaller than s squared. And if we fill in that Taylor series into the limit, we get a limit that we can actually compute using Wolfram alpha and see, it is exactly the characteristic function of the normal distribution. So we've proven that in the limit Zn approximates the normal distribution. Now, I can almost hear you thinking that's all very nice, but why? Well, in the beginning of this module, I promised you that I would show you a way in which you could scientifically refute the hypothesis that an experiment behaves according to a certain statistic model. Now, if you take as a statistical model the idea that an experiment is the hypothesis that an experiment has a mean mu, and you perform a number of experiments, then you get some kind of running average. And we know that that running average is distributed now along a normal distribution. That means that we can compute the probability that there is a deviation between mu and the value that we measured. And we can compute also the probability, in particular the probability, that that deviation is equal or larger than the deviation that we actually found. So, what does that mean? Well, for example, if we sum up 500 rolls with a 6-sided die and we find a total of 1848, then this gives an average of 3.696. While we expected an average of 3.5 with a variance of 2.9167. So the value of Zn in this case is the square root of n times x bar minus mu divided by sigma is the square root of 500 times, well, this 6.696 minus 3.5 divided by sigma, that's the standard deviation, is 1.7078. That gives us a value of Zn of 2.5662. The approximate probability of finding Zn, I say approximate because this is a limit, but the approximate probability of finding Zn to be bigger than this 2.576, you can compute by computing the area under the probability density function. So you have the probability density function of the normal distribution, and you compute the area of these two tails. We use MATLAB for this, or you use a standard table in any statistics book. The reason why we don't have a formula for this is because even though we have a formula for the probability density function, there is no algebraic formula for the cumulative distribution function of a normal distribution. So you will always have to approximate it. If you compute this probability, you get to 0.01, which means 1%. What does that mean? Well, that means that in 1% of the cases, when you perform an experiment like this, throwing that dice 500 times, you will find an average that lies somewhere in these tails. That means that there is a 99% probability that something else happened. And the only explanation for something else would be that our model is wrong. So there is a 99% probability that either we did not do our experiments in an identically distributed and independent way, or the distribution is not what we expected. So if we're convinced that our dice rolls were actually independent, then that means that they are not distributed the way we thought. We have proven with 99% probability that our original model is wrong. So that is the value of the central limit theorem. And you may not be surprised that you can actually expand that central limit theorem a little bit further if you want. For example, there are versions of the central limit theorem that do not require that you have identical distributions throughout all your experiments. As long as the distributions that you're using themselves converge to a distribution that has an expected value, you will still be okay. Also, if the distributions are not completely independent, but their covariance remains in check, remains small enough, still something like a central limit theorem may hold. If you want to know all these advanced versions, have a look at statlag.com or do some further research. For our purposes, this classical central limit theorem is sufficient. Another thing is that I used the central limit theorem in this video as a justification for the intuition that if you have a series of experiments, the average tends to the expected value. This actually is in mathematics more generally known as the law of large numbers, which is a theorem on its own, and it, for example, does not even require the standard deviation to exist. There is a weak law of large numbers, which says that the running average of a series of IID variables approaches the expected value. This is what the central limit theorem does as well. But there is also a stronger version of the law, which requires still just the expected value of the sequence to exist, which says that the probability of picking a series of IID variables that does not converge to the expected value is 0. Of course, series of experiments exist that would not converge. For example, if I would throw a coin, as I did in the beginning of this video, and I would throw heads, tails, heads, heads, tails, tails, heads, 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 tails, 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 and so on, longer and longer series of the same thing, that sequence in itself would not converge. But the strong law of large numbers says that the probability of picking such a sequence is 0. In other words, if such a sequence appears somewhere, that's not a coincidence. Because the central limit theorem is so important in statistics, I wanted to spend a separate video on it. In the next videos on hypothesis testing, you'll see how it is going to be used in practice and how you can use it for the assignments that come with this module.